Welcome back, ladies and gentlemen. Last time we learned about ions. We learned about the idea that atoms want to fill their valence or reveal a full valence. We learned about the idea that there are cations and anions. Anions, of course, are negative, and cations are positive because they have paws like a cat. And we learned all of this in relation to the periodic table, and we learned about the pattern in the table that we're going to be able to make use of, about the fact that the finish line of the whole ionic race is this final family. Everyone wants to be a noble gas where they don't have to do anything, they don't have to work for a living, everything's nice and relaxed and comfortable. In order to do that, the elements that are close to it will move towards it. So the fluorine family will move one step to the right, and the oxygen family will move 2 steps, the nitrogen 3 steps. Carbon, it's a bit weird, you can go 4 steps one way or 4 steps the other way, just like the other metals where they go this way, and they go 1, 1, 2, 3. Because again, reminder, the periodic table is a cylinder, not a flat surface, so it wraps itself around and the numbers line up. So I can go left or I can go right without any problem whatsoever. So what does this mean for our purposes? Well, hopefully now that we are a little bit more familiar with the movement of electrons and the general behavior of atoms to turn into ions, now we can talk about compounds. Because we started this whole thing, we prefaced it on saying that atoms want to become ions, they want to fill their valence, and then once they do become ions, they get attracted to each other, like two sides of a magnet. And that is exactly what we're going to be talking about now, ionic bonding and the creation of compounds. Now, in order for us to be able to do this, though, it would be important for us to know sort of the style or the notation of chemistry, the way of writing things, right? When you do math, you don't write it out with words, right? You don't write the number 4 as the word 4, you put it as 4, very quickly, very simply. In the same way, chemists don't want to have to write out the names for all of these chemicals in order to work with them. Instead, what they do is they will put them as symbols or formulas. Now, the reason, of course, for doing this is because chemists are A, lazy, and B, nerds, which means it is very easy to get a bunch of lazy nerds to do something that is a lot less work. And most lazy nerds already know math, so they use a lot of math terminology, but they tweak it a little bit because they don't want to be too much like math. Like, that's for other people. They want to be special. So we've already seen how to draw out or how to show with a Lewis structure how these atoms will look, right? So now we're going to see how you can put these things together. Now, let's take an example. Here's a chemical formula that you probably know incredibly well. You've probably seen it before. H2O. Now, admittedly, those in the audience who are a little bit more up to date on chemistry will know that's not an example of ionic bonding, that's an example of covalent bonding, but that's okay. I'm using this one because it's one that everyone probably knows, not because it necessarily fits with ions. H2O, what does that mean? Well, that means water, of course. But the information it's telling us has other things of use. First of all, it's telling you that hydrogen is present and that oxygen is present, right? It tells me the pieces that make up water. But what else does it show me? Well, it also tells me how many of each there are. I know that I have 2 hydrogen and 1 oxygen because there's a 2 here. So what we see is that the numbers of a chemical formula tell you what pieces you have to put together. There's a huge difference between H2O and H2O2. H2O2, you might be familiar with it actually. It's called hydrogen peroxide. You might have put it on a cut and it bubbles up and fizzes. You drink that, well, it won't go well. Let's put it that way. Water, you need to live. The only difference is 1 extra oxygen. Now, you'll notice something else about the 2 in H2O is that it is a subscript. Subscript means that it is below the script. Sub means below, so subway is the way below the ground, or a sandwich restaurant. Subscript is a script so like writing, below the line of writing. So this here is a subscript, and what we see is that subscripts are used to mark connection. What do we mean by that? Well, instead of putting it as a subscript, let's say that I wrote it like this. I'll put it in another color to make it very distinguishable. Let's say I did this, 2HO. Or let's say I did H2O. In these cases, by the chemistry language, there's no real indication that these H's and O's are connected in any way. All right? Whereas this one up here is telling you quite clearly they are connected. If I were to actually draw it out really quickly here, just so you could see it, it would look something like this. The subscript is telling you that the H's and the O's are joined together in some way. Okay? So that's a pretty easy one, but it's also not an ionic one. So let's do some ionic ones, okay? Like we can't all just hang out with stuff that we're very familiar with. We'll get our magnets out of the way. We might need them in a bit. So for another example here, let's go with Li2SO4. Okay, so once again, what information does this chemical formula tell me? Well, I've got a couple different things. I've got Li, but the I is lowercase. We must remember that elements always start with an uppercase letter. So even though there's an I there, and even though I could find an I on the periodic table, that I is part of the L. What do I mean by that? Well, look, there's an I right here. Down low, it's called iodine. But I'm not telling you that I've got some L thing and some iodine thing. I'm telling you I've got Li, which is lithium. So the fact that this is a lowercase and this is an uppercase is telling you something pretty significant. Now, lithium is not the greatest example for this. I mean, it's a great example for ionic bonding, but it's not a great example for the whole capital letter thing because there isn't really an L element. But there is a good example in this one, and that's the sulfur. Let's say that I had two different chemicals, right? And one of them looked like this, and one of them looked like this. They both have the same letters, but they have completely different meanings. In this particular case, I've got two capital letters. That is two separate elements. I've got sulfur, and I've got iodine. Small aside here, right? I've spelled sulfur with a PH. That's the standard Canadian or British spelling. If you want to do it with the standard American spelling and go with an SULFUR, that is fine by me. Either one works. People will know what you're talking about. I'm going to stick with the PH, though, because I live in Canada. Anyway, these are two separate elements, but this one is not. This one here is silicon. A completely different element. So whenever you're looking at the different formulas, take a look to see if there are any lowercase letters. If there are lowercase letters, that means that the two letters are combined, like in the case of lithium or silicon. In the case of sulfur here, though, this SO, those are two separate elements. Now, we have to be able to properly parse this, to properly figure out what it's saying. Remember, subscripts, as we just discussed over here, means they're connected, and they also tell you how many there are. So in this particular case, I'm going to have lithium, and there are two of them. I'm going to have some sulfur, and there's one of them, because there's no number written here in any way, so there's just a single sulfur. Then we've got oxygen, and there's a 4 underneath, so that means there are 4 oxygen. And, of course, because they are subscripts, they are all connected together. If I were to try and draw this one very, very roughly, I might look something kind of like this. I would say this is not completely accurate, but you know what? For our purposes, they will do well enough. So they're all connected together in some way. Okay, You'll notice, of course, this is one of those things that people always get confused with, is that they generally want to make it so the 4 applies to the sulfur as well, and they want to say there are 4 sulfurs. There are not. The subscript tells you exactly which element has more than one, and that all those elements are connected. Now, it gets a little bit more complicated, though. Let's take a look at our next example. Our next example here is going to be this guy. Which number are we looking for here? Yeah. We got brackets showing up. What in the world are there brackets for? Well, again, remember, chemists are nerds. So in math, you learn that brackets are ways in which to group different terms together, right? Like if I've got some numbers and I want to do something with them separate from everything else. So for example, I might have, 2 times 6 plus 4, right? That would be a way that we use brackets. Now, this is pretty much the same thing that we're doing with brackets in this case. We're trying to say that there is sort of something you're going to do math to everything in the brackets combined. Now, that said, there's a bit of a difference in that we've got our 2 down low over here rather than out front like we do here. The reason for that, of course, is because subscripts tell you things are connected. So this guy over here might look something like an Fe with some S, O's, and then another one like this, S with some O's attached. Again, not very accurate for what this should look like. If you go really deep into chemistry and you start learning all of the structures and things, that's going to be like, no, Mr. C, that's not right. But for our purposes, it gives a point across. They're connected in some way. So the thing is you'll notice, is that as I drew it, I've got 2 sulfurs, and I've got 8 oxygens in total, 4 up above, 4 down below. It's basically me saying that I've got 2 of all the things in the brackets. Now, the reason we do that is because it lets us know that the SO4s are come as a package deal, right? They're like, you reach in and you get to pull them out, and they're all here together, all in one place. But that's not the only way to do this. But that'll be for the last example. Well, let's not get ahead of ourselves, Mr. C. Again, what do we see here in terms of the numbers? We know that there's going to be 1 of these FEs. I wonder what that is. There's going to be 2 of the S's, and there's going to be 8 of the O's. Fe, can you find it? Have you found it already? Do you know what it is? It's a weird one, or so it appears to be weird, because Fe doesn't seem to match any particular name, right? Usually the symbols and the names are close to each other. But Fe is right here in the middle of the table in this section that we haven't really talked about much, and it says the word iron underneath. Now, even somebody who can't spell at all, like Mr. C, won't spell iron with an Fe. So what's going on here? Well, what's going on here? Well, iron didn't always used to be called iron. Turns out there are other languages in the world, and one of those other languages was one called Latin. And the Romans, who spoke in all their Latin, ended up talking about ferrum or ferrous. And both of those are in Latin, which you'll see immediately matches the Fe. And you'll find that there are actually a bunch of different elements on the table that the symbol doesn't quite match up. Usually if that's the case, it's because Latin's involved, usually, but not always. Other famous ones, gold is Au, which is aurum. Silver is Ag, which is argentum. Copper is Cu, which is close, but not quite. Cu is cuprum or cuprous. Lead is Pb for plumbum. That's where plumber comes from. There's a whole bunch of these. Tin is Sn for stannum. A lot of these, of course, are older metals that people have been using for a really long time, but there are a couple more modern ones. Tungsten, used in incandescent light bulbs, which you really won't see very much anymore, but back when Mr. C didn't have gray hair, that was very common. Tungsten, its symbol is W. There's no W in there at all. And we can't blame this on the Romans, because tungsten is a fairly new discovery as far as an element goes. But instead, we can blame this on the Germans, because the Germans are the ones who discovered it, and they named it after the guy who discovered it, Wolfram, because, it's pretty cool. The name's got a wolf in it. Why did the English decide to go with tungsten instead? No idea. That one I don't know, but there it is. Anyway, this, of course, is showing us that we have a group, and the group, there are two of that group, because they're connected. But we got one more possibility in front of us, one more unusual situation. We'll put it down here in the middle so we can compare side by side. Our fourth option that we will discuss is going to be this one. Now I have a number in front. Now, okay, if I ignore that part there, cover it up. That part there should be easy, right? How many Ca? What's Ca? We'll have to look it up. We get our periodic table, we check. It's calcium. Okay, so I've got one calcium because there's no number right there. And then I've got Cl. Now, it's a lowercase a and a lowercase l, so that's how we know there are just two elements here, right? Otherwise, if they're all capitals, then we have to do some other weird thing. Cl here is chlorine. It's on the far right side of the periodic table. It's underneath fluorine. Cl, of course, has a 2, so that means there is 1 calcium and 2 chlorine. But then I got a 2 in front. What does that mean? Well, let me draw something again. Let's say I've got myself a calcium, and I'm going to draw my calcium connected to chlorines. Why are they connected? Subscript. Again, think about math. When we put brackets around something, we're saying that we're going to do the number on the outside, the coefficient, we're going to do that to the whole thing inside too. So what am I saying? There are 2 CaCls. CaCl2s, I should say. Now, why did we bother putting it on the outside instead of a subscript like we did here? It's because of this first rule. Subscripts are used to indicate that they are connected. These are not connected. They are 2 separate chemicals. An analogy. My marker. It's got 2 parts. They're connected. I have 2 markers. They both have 2 parts. They're both connected to themselves, but they're not connected to each other in any way. So this number of markers would be said as having 1 lid, 1 marker body, and I would then put brackets around it and put a 2 in front to mark the fact that there are 2 markers, each of them independent of each other in every way. Okay, that's a lot, and we're not going to have to deal with most of these right away, but now you understand, I hope, the basic language of chemistry when it comes to writing out formulas. With that in mind, we're going to explore writing ionic formulas. Ionic formulas, of course, are the formulas for ionic bonds, the formulas that are made between cations and anions, between positive and negative. Let's do an example. A very simple starting example, we're going to do sodium plus chlorine. Now, I don't want to draw a Bohr diagram. They're a lot of work, and there's a reason we showed you guys Lewis. So we're going to pull out some Lewis structures. Remember, sodium, we get out our periodic table and we have to check here. Sodium is located in the first family, which means it has 1 valence electron. So I put 1 electron like so. Chlorine, as we just mentioned, is in the halogen family, the 7th family. It's underneath fluorine by 1. So that means chlorine is going to have 7 electrons. Why 7? Because it needs 1 more to fill up. I almost filled it up already. I almost drew it into an 8th. So that is the atoms that I started with. But we're not going to stay with that because, as we know, the chlorine wants a full shell and the sodium wants to get rid of that extra electron to reveal the full shell underneath. They both kind of want the same thing. He wants 1, he wants to get rid of 1. So what's going to happen? They're going to cooperate. The sodium is going to say, hey, buddy, here you go. Take it. Take it with respect. Enjoy. What's this going to do? Well, this guy here is now going to be minus. And this guy over here is now going to be plus. The net result is that the two of them combine. They attach together. We would show that by going Na plus Cl minus, which leads into NaCl. There's one of each, as we just learned. They are connected, but there's no subscripts necessary here. Okay? That hopefully seemed pretty straightforward. Let's try another one, right? Just to warm ourselves up. Let's go with Mg plus I. Okay, well, we need to find them first of all. Periodic table time, we pull it out, we take a look, and we see Mg is underneath Be in the second family, which means it's got two valence electrons. So I'll put one there and one there. Iodine, well, we hopefully know where that is. We've talked about it a bunch today. It's over here under the halogen family. Iodine is right there. It's way down in the list, but it doesn't matter how far down it is. Which family is it in? Halogen family, 7 valence electrons. How many electrons does it need to get? It's one step away from the end, so it needs to gain one more. All right, so 1, 2, 3, 4, 5, 6, 7. Okay, much like before, this guy wants to give, this guy wants to take. Remember, the table is divided by this staircase into metals and non-metals. Generally speaking, everything on the left of this staircase line is going to give electrons. Everything on the right is going to take them. Right? That's what this whole line right here is. 3, 2, 1, 3, 2, 1. Okay, so he's going to give away an electron. He's going to go, hey, buddy, here you go. Have fun. Enjoy. He becomes negative because he just gained one more electron. This iodine is happy. It has filled its valence. It is finished. It can go relax on the couch. But the magnesium cannot. The magnesium still has an extra electron left over that it needs to get rid of in order to reveal the full shell. So it has to give it to somebody. Well, it can't just like dump it on the floor. Somebody has to take it. So what do? They find another iodine somewhere in the room, and they tell the iodine, hey, look, your friend took one, you have one. I brought enough for everyone to share. Now they're both negative, and this guy over here is going to become positive. He lost 2, though, so he's going to become 2 plus. Because I lost 2, I took 2 steps to get to the end, right? I started here, the magnesium location, then I went 1 step, and then I went 2 step up here to finish it off. Because again, remember, it's a cylinder. Now, when it comes to writing this, what we're going to see is that we're going to have Mg2 plus 2 I minuses. Because again, they're not connected yet, and I'm going to make them connected. And what do I get? Mgi2. A subscript 2 to make them all connected. What happens if we have an anion taking electrons from 2 different metals? What would be an example of that? Maybe something with good old oxygen, right? Oxygen has 6 electrons in total. They've got 2 spaces for electrons. And we're going to pair some oxygen with, let's do something very simple. Let's say lithium. Lithium's in the first family, so it should have 1 electron. Okay, so much like before, the lithium will donate an electron. It will pass it over here to the oxygen, and the lithium will be quite happy with that. It'll be a nice positive. But the oxygen's not happy. The oxygen is still hungry for more. So what's going to happen is it's going to find another lithium. And it is going to take that lithium's oxygen, that lithium's electron as well, making it so the lithium becomes another positive, and the oxygen becomes 2 negative because it has gained 2 electrons. Now, if we keep going with this, of course, we're going to get that there is 2 of the lithiums, and they are 1 plus each. And then there is 1 oxygen, which is 2 minus. I combine those two together, and of course they're all connected, so subscripts come out, and we end up with Li2O. There we go. We can see that's very similar to the MgI2, but now of course we've got 2 metals as opposed to 2 nonmetals. Now, if you remember when we talked about the pattern in the periodic table, there can be anywhere from 1 to 4 different amounts of electrons transferred in some way. So these are just some simple ones to start with. You're going to find some much more complicated ones coming up. What happens when I put aluminum plus oxygen, for example, or sodium plus phosphorus, or nitrogen plus lithium? Lithium would be better. Aluminum would be easy. You'll see all of those and more as you work through your practice. And you're going to need a lot of practice. So, with that in mind, I will leave you there, and I will see you next time.